We're going to be talking now about indirect solar energy. That's energy where we're not dealing directly with the sun, but we're dealing with a flow of energy that is driven by energy from the sun. So there's been some transformation of that solar energy into some other form. So here's our figure that shows the distribution of the solar energy as it comes into the Earth. Some of it's reflected. Most of it, the remaining part, ends to just going into heating up the planet. And about a third of that remaining part, or a quarter of the total, 23%, goes into evaporating ocean water. And that creates water vapor, which forms clouds. And some of those clouds end up uh, moving over land, and then that energy is released and the water falls back down, but it doesn't fall all the way back down to the oceans. It falls on land, which is above ocean water, and it then has gravitational potential energy. So this circuitous route of sunlight evaporating a water molecule, the water molecule rising up into a cloud, wind carrying it over a mountain, and then condensing back into a water droplet and falling down on that mountain, and it is now higher, part of a river, and as that river flows downhill, that water's got gravitational potential energy. And that may seem like a ridiculously complicated and unlikely source of energy, but as we saw in the previous module, the amount of energy available in sunlight is huge, and a significant portion of that, 23%, goes into this evaporation of water. So again, a tiny fraction of that would still be a significant amount of energy. Remember that only 0.01% of all of that solar energy would be enough to supply all of humanity's energy needs. And fully 23% of it is going into this evaporative process. So that's the basic energy transformation story that leads to what we call hydropower. So this chart shows the uh, total energy supplies used by people. About 9% of human energy comes from indirect solar, and 83% of that 9% is in the form of hydropower, and the rest is wind, which we'll also talk about, and biofuels, which I would include wood and waste in the biofuels. So let's take a look at how hydropower works. That's the first part of chapter 10 of your textbook. Remember again that you've got resources that you can go to in the switch videos. But let's start by taking a look at this hydrologic cycle. That's the motion of water between the ground, the oceans, and the atmosphere. The numbers on this are estimates of the total amount of water flowing each year in thousands of cubic kilometers. So that's a huge amount. Kilometers, about 6/10 of a mile. So imagine a cube, square kilometer, but then going up into the air another kilometer. That's a cubic kilometer. Fill it with water, and then 1,000 of those would be one on this chart. So this 450 arrow coming up from the oceans, that is the evaporation of ocean water into the atmosphere by that's powered by sunlight, the absorption of solar energy in the oceans causing that to evaporate. 90% of that just falls straight back down into the ocean. That's the 404 that falls straight back down into the ocean. There's an additional 71,000 cubic kilometers of water that is evaporating into the atmosphere from water on land. That includes lakes and rivers, but also the land itself can be moist, and water evaporates out of that and goes up into the atmosphere. So that gives us 521. 450 plus 71 is 521 going up into the atmosphere, and then we have 404 falling back down onto land, but 117, the remainder of that 521, falling on land. So we have a net transport of some of that water vapor falling back down onto land, and that water needs to make its way back to the oceans, or the oceans would empty out. So that water just runs downhill, 44,000 cubic kilometers making their way back into the oceans through rivers, and a tiny amount through groundwater. So to summarize, energy conversions in hydropower, we start with the sun. The sun heats up water on the surface of the earth, such as in the oceans. It causes it to evaporate. So there's a phase change. The water goes from liquid to vapor form. That warm water is in warmer air, which is less dense and therefore buoyant and rises due to convection. That water vapor at higher altitudes, it's cooler. It condenses back into droplets of water called rain, and those droplets then fall. They're no longer light enough to be suspended in the air. During that process, there's some horizontal motion of the air that means that some of those droplets of water end up falling on the ground. So that water now has gravitational potential energy, and as it runs downhill in rivers, that gravitational potential energy is converted to kinetic energy. Well, that's a high quality energy. I can just put a water mill in that flowing water, and that kinetic energy of the water gets directly converted into the kinetic energy of that mill. And before we were using it to generate electricity, that was used to do things like grind grains and run other mechanical um, installations just using the power of that water flow. To calculate gravitational potential energy, here is your equation. Gravitational potential energy equals m times g times h. M is the mass, that's the amount of water that you're dealing with at some height h above some reference surface. Kinetic energy of the water is 1/2 times m times v squared. So if I have a kilogram of water at a height of 1 meter above the ground, I would have m equals 1, h equals 1, g is about 10. I'd have 10 joules of energy. If that all got converted into kinetic energy, I'd have 10 joules of kinetic energy becomes 1/2 mv squared. And I could, if my m was 1 kilogram, that would give me a speed of the square root of 20, which is about 4.5 meters per second. And that's how fast that would be falling. So where are the hydropower resources in the world? Of course, it just depends on where water happens to fall and if there are mountains and hills so that the water falls downhill. Uh, Hydropower resource is illustrated in the lower left-hand corner of this graph. Uh, Solar, you can see in the right-hand graph, is more evenly distributed. It's concentrated primarily around the equatorial regions, so Asia, Russia, Western Europe don't have as much because they're farther north and cloudier. But on the left, in hydropower, you can see that most continents have fairly large resource of hydropower with the exception of Africa. Within the United States, most of the potential for hydropower is in the Pacific Northwest. It's very rainy up there, and in the Great Lakes regions where it's also rainy and there are big flows of water. And there's much less in the desert Southwest region of the United States where there's just less water flowing. So if we look at where the hydropower plants are, you can see there's virtually none in Florida. Why? Florida's flat. So it rains a lot here, but there's no H to give you gravitational potential energy from that rainfall. On the other hand, we have lots in the sort of Appalachian Mountains and in the Rockies and in the Sierra Nevadas and in the Pacific Northwest. The percent of electricity that comes from hydropower for different countries, you can see that Congo, which has a large river running through it, gets essentially 100% of its electricity from hydropower. Norway, which is very mountainous, is a small country, so it doesn't have huge electricity needs to begin with, also gets nearly 100% of its electricity from hydropower. Worldwide, that's the little bar on the far right, you're down around the 10% level. In the United States, somewhere less than 10%. If we now take a look at the potential of getting electricity from hydropower, uh, this chart shows it broken down by continent, and the dark bars show the potential of hydroelectric power that could be obtained, and the pale bars show the actual amount that is being drawn in each of those continents. So you can see that Europe has essentially maxed out their exploitation of hydropower, and North America also, there's not a lot more potential to go there. I'm going to go back just to clarify something I said on this earlier slide. This is how much is being exploited at the present time, and that corresponds to these pale bars in this chart. But South America, South and Central Asia, Asia, and Africa have a lot of untapped potential for hydroelectric power. So I already alluded to, before even thinking about electricity, you can convert that nice gravitational potential energy that this water has by virtue of being uphill from where it's going to go. That kinetic energy, I can convert some of it into the kinetic energy of a wheel. So this was used for factories and for grain mills. But now we can use that to be the turbine that is turning in an electric generator. So you build an artificial, you build a wall or a dam that causes water to pile up behind it, and that increases the value of H in the equation for gravitational potential energy. And then you let that flow of water uh, through the dam, and it flows down, and you're converting gravitational potential energy to kinetic energy, goes by a mill of sorts, which causes it to spin. You just hook that up to an electric generator, and you've got electricity. So remember, the equation for gravitational potential energy was mass times the number g, 9.8 meters per second squared, times the height. This slide shows two different uh, sort of styles of dam. On the one on the left, there's a fairly large H. The water is falling through a large distance. And the one on the right, there's a large amount of water going through there. It's a very large dam, very large river, and that's generating 22,500 megawatts, or about the equivalent of 20 coal-fired power plants. And the next slide from your book shows another sort of comparison. The Hoover Dam on the Colorado River is not a huge flow of water, but it's a fairly large value of H. The example on the left, there's not a very large value of H, but there's a large flow of water through there. And finally, you have an example of some of the largest hydroelectric power plants in the world.